Today we're going to look at section 3.4, which is called Zeros of Polynomial Functions. So our objectives today, we're going to use the rational zero theorem to find all possible rational zeros. We're going to find zeros of a polynomial function, and then we're going to solve these polynomial equations. So the rational zero theorem says this: if f of x equals a sub n x to the power of n plus a sub n minus 1 x to the n minus 1 power plus, and then it keeps going until it gets down to a sub 1x plus a sub 0. It has integer coefficients and p divided by q, where that fraction is reduced to the lowest terms, is a rational zero of f. Then p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. Okay, so the numbers that are in front, we want to take essentially the constant, which doesn't have a variable, and that's going to be where we'll find all the factors of that. And then we'll look at the leading coefficients and find all the factors of that, and we're going to put the p's on the top over the q's on the bottom. And those are going to be how we're going to figure out zeros of our polynomial. So let's take a look at an example. It says list all possible rational zeros of f of x equals x to the third plus 2x squared minus 5x minus 6. So like I mentioned, notice how this is in standard form. It goes from the biggest degree down to the smallest. So that was essentially that big definition that I was talking about. I need to know what is the leading coefficient number and what is the constant at the very end. Well, x to the third is the first term. It has a lead coefficient of 1. That number is going to be representing either p or q. And so in this case, it represents q. The number that is at the very end is going to represent our value for p. And so I don't care if it's positive or negative. I'm just going to always write it as a positive number because I'll explain in a second. What we're going to do is when we're listing all possible rational zeros, we're going to be putting plus or minus signs in front. So that's why it doesn't matter if p or q actually starts positive or negative. Eventually, it's going to be listed as both a positive and a negative. Okay, but it wasn't just me recognizing those two numbers, but it was me, first of all, listing all the factors of those numbers. So 6, I can list all the factors. I know that I can multiply 1 times a number to get 6, 2 times a number to get 6, 3 times a number to get 6, and 6. So 1, 2, 3, and 6, those numbers are going to multiply to get me 6. 1 times 6, 2 times 3. When I'm looking at q equaling 1, well, the only way to multiply to 1 is 1 times 1, so I don't really have to list those factors. It's just 1. So the definition says that we want to have p being divided by q. That's how we want to set everything up. Okay, so all my possible zeros, possible rational zeros, is going to be me taking a plus or minus sign, and then I want to do a combination of p divided by q. So I'm going to take all the numbers for p and put them over all the numbers for q. Well, in this case, since q is just 1, if I divide by 1, it's not going to then change anything for p. So I have a 1 for p and I've got a 1 for q. 1 divided by 1 is 1. So I'll have both positive and negative 1 as my possible rational zero. Then I'll put my plus or minus sign again, and now I'm going to move on to 2 for p. Q is still 1. Well, 2 divided by 1 is 2. Plus or minus. Move on to the third p value, which is 3. Put p over q. 3 divided by 1 is 3. Plus or minus. Then move on to the next number for p, which is 6. 6 divided by 1 is 6. So these would be all my possible rational zeros. And I'm done. Let's take a look at another example. we're listing all possible rational zeros of f of x equals 4x to the fifth plus 12x to the fourth minus x minus 3. So once again, this is in standard form. It goes from biggest degree down to the smallest. I need to identify what p is and what q is. So remember, p is represented as that very last constant that doesn't have any variables. And I don't care if it's positive or negative. I'm just always going to list it as a positive to begin with. So the last number is 3. I'm then going to look at that very first leading coefficient number because that's going to represent q. And so that looks like it's 4. So I want to find all the numbers that multiply to 3 and list them out. Well, 3 is a prime number, so 1 and 3 are the only ways to multiply to get me 3. Then I want to start listing all the ways to multiply to get me 4. Well, that would be 1, that would be 2, and that would be 4. Because obviously 1 times 4 gets me 4, 2 times 2 gets me 4 as well. So with those numbers, now I can think about P over Q to list all possible rational zeros. Okay, and so I always want a plus or minus sign in front. Once again, I'm thinking P on the top, Q on the bottom, and I always want to reduce the fraction if I can. So I'm going to start with the P being 1 and the Q being 1. Well, 1 divided by 1 is 1. I'm then going to move on to the 3 for P and stick with the 1 for Q. Well, 3 divided by 1, I'll have positive and negative 3. Okay, I don't have any more P's on the top, and so that means I'm done by putting it over 1 for Q. Now I'm going to move on, go back to the 1 for P, and I want to put it over 2 for Q. Well, 1 over 2 is as reduced down as possible, so plus or minus a half is another possible rational zero. I'm going to move on to the 3 for P, keep the 2 for Q. 3 over 2 is as reduced down as I can get, so positive and negative 3 halves. Don't have any more P's, so I'm going to go back to 1 because now I'm going to move on to that very last Q. Well, 1 over 4 can't be reduced down any further. And then we also have 3 over 4. So these are all the possible rational zeros. All right, so once we understand how we can find all possible rational zeros, that's going to help us now find zeros of a polynomial function. So in the past, I've always given you a 0, and that's how we've been able to then find all of the zeros. Sometimes I'm not going to give you any zeros, and it's going to be up for you to determine all of the missing numbers. So here are our steps. We're going to list all possible zeros just like we did in our first two examples. So we identify P, we identify Q, we do plus or minus P over Q. Then we're going to test each zero using synthetic division until we can find a remainder of 0. Okay, because remember, if we get a remainder of 0, that means that that number is a factor, or in this case, a 0. And we want to be determining all the different zeros that will then lead to us being able to factor that polynomial. We're going to write the new polynomial 1 degree less than the original polynomial, just like we have in the past. We will then continue testing zeros until we can get down to a quadratic, so till we can get to an x squared term. Because once we get to x squared, we're going to be solving either by factoring, if it's factorable, or if it's not factorable, we'll do the quadratic equation to get the rest of our solutions. Let's talk about strategies, because we could potentially list, 20 different possible rational zeros. There's no way we're going to want to test all 20 of those numbers. So let's look at some strategies. I would always start with the number 1. Okay, if that 1 doesn't give us a remainder of 0, we're either going to move up towards positive numbers and test those, or we're going to move down towards negatives. But I'm not really going to jump around positive, negative, positive, negative. I want to either stick them with positive numbers or stick with negative numbers. So there's going to be a rule for us to determine if we should go positive or go negative. So we have something called the lower bound rule. It says when signs alternate and we didn't get 0 for a remainder, there's no way we can go any smaller than that number. So if we get like a positive, then a negative, then a positive, then a negative, but then our remainder is not 0, we know, okay, whatever number we tested, we're not going to want to go any smaller than that. We also have something called an upper bound rule. That's when all the signs are the same and we didn't get 0 for a remainder. So everything's either positive or everything is negative, but 0 is not my remainder. That means we don't want to go any bigger than the number that we tested. All right, so let's take a look at an example. We're going to find all the zeros of f of x equals x to the third plus 8x squared plus 11x minus 20. So notice that in this problem, they did not give us any zeros. So right off the bat, I'm not going to be able to do synthetic division. First and foremost, we have to figure out what are all my possible zeros. So that means we need to identify the P and identify the Q and figure out the factors. Well, Q is going to be 1. So that's something that's nice. We're only going to have factors of P over 1. So just essentially all our possible rational zeros are the numbers that multiply to get us 20 because that is our P value. Okay, so all my possible zeros, possible rational zeros, I should say. Okay, so P over Q, and we want plus or minus signs in front. So I know I can take 1 times something to get 20. So plus or minus 1. And once again, it's going to all be over 1. So that's why I'm not going to write it as a fraction. I know that 2 is a factor of 20. 3 is not, but 4 is. 5 is. 6 is not. 7 is not. 8 is not. 9 is not, but 10 is. Okay, and then the last one would be 20. Because think about it. It's 1 times 20, it's 2 times 10, it's 4 times 5. And because those are all over 1, I don't have to make it a fraction because we're thinking P over Q, everything's over 1. Okay, so those are all my possible rational zeros. So 2, 4, 6, 8, 10, there's 12 possible zeros for us to test. So like I mentioned, I would always start with the number 1. So doing synthetic division, I put the 1 on the outside. I'm looking at my f of x function. I don't see any missing terms, so I'm going to put all of my numbers. So 1, 8, 11, and negative 20. I'm going to bring down my lead coefficient. 1 times 1 is 1. Add that up, I get 9. 9 times 1 is 9. Add that up, I get 20. 20 times 1 is 20. Add that up, I get 0. So nicely done for us. We got a 0 for our remainder. So when we're asked to list what our zeros are, I know that one of my answers is 1. Remember, this is degree 3. So that means we should have 3 zeros or 3 answers. And we just found one right off the bat. So now I get to take those numbers, 1, 9, and 20, and I get to write it 1 degree less than that x cubed. So we'll have an x squared plus 9x plus 20. And we're solving for solving for x, so we have to set that equal to 0. So remember our step said, get it to a quadratic, so then we could either factor or we could do the quadratic formula. So luckily for us, this is a factorable quadratic. I can find numbers that multiply to 20 but add to 9. That would be positive 5 and positive 4. So x plus 5 times x plus 4 still equals 0. I have to set each of those equal to 0 to finish solving for x. So that means I'm subtracting the 5, I'm subtracting the 4. So my other 2 zeros to get me my 3 zeros would be negative 5 and negative 4. So my 3 answers, 1, negative 5, and negative 4. All right, let's take a look at this example. We want to find all the zeros of f of x equals x cubed plus x squared minus 5x minus 2. So we want to list all possible zeros, all possible rational zeros, I mean. Which means we need to identify our p and our q. So p is going to be the last number, q is going to be the first number. So 2 and 1. And I'm thinking, all right, possible rational zeros, p over q. Well, for 2, it's 1 times 2. And obviously, if q is 1, then I know that I'm not going to have any fractions again. So 1 over 1 means that we'll have 1, and 2 over 1 means we'll have 2. So plus or minus 1, plus or minus 2, there are 4 possible rational zeros. Like the directions and steps say, let's start with a positive 1. I'm looking at my f of x function. I don't see any missing terms. So we'll have 1, 1, negative 5, and negative 2. So bring down the 1. 1 times 1 is 1. Add that up, I get 2. 2 times 1 is 2. Add that up, I get negative 3. Negative 3 times 1 is negative 3. Add that up, I get negative 5. So unfortunately, I did not get a remainder of 0. So that means that now my strategy is I either move up to positive 2 to keep with the positive numbers, or I move down to negative 1 and start the negative numbers. Okay, it's a guess and check process at this point. So let's just try going up to the other positive. So let's try going up to positive 2 and seeing what we get. So I'm going to bring down my Lie coefficient of 1. 1 times 2 is 2. Add them up, I get 3. 3 times 2 is 6. Add those up, I get positive 1. 1 times 2 is 2. Add that up, I get 0. So I guessed correctly. I moved up to positive 2, and so I got one of my answers to be 2. That means I get to take those numbers. I get to write it as 1 degree less. Remember, if this is degree 3, that means that we should have 3 zeros. And if I get to write it as 1 degree less, that means now I'm dealing with x squared plus 3x plus 1. We want to solve for x that equals 0. So because it's a quadratic, we either can factor or we can do the quadratic formula. Well, in this problem, because I can't factor, because 1 times 1 is the only way to multiply to 1, but that can't add up to 3, we have to do the quadratic formula, which remember, the quadratic formula, when we're solving for x, we're thinking negative b plus or minus, under the square root, we want b squared minus 4ac, and this is all over 2 times a. In this particular problem, a is 1, b is 3, c is 1. So I'm going to plug those numbers in. So we're going to have negative and then b plus or minus under the square root. We'll have our b being squared minus 4 times a times c. And that whole entire thing is all over 2 times a. So we'll have a negative 3 plus or minus under the square root. 3 squared is 9. 4 times 1 means that we'll have negative 4 underneath the square root. This is all over 2. If I subtract 9 and 4, I'm going to get 5 under the square root. Well, I can't take the square root of 5, so I can't simplify any further. So it looks like negative 3 plus or minus the square root of 5 all over 2. Those are my other 2 zeros. Because of that plus or minus sign in between, those are 2 answers. 2 is my third answer. I should have 3 zeros. I am done. All right, let's take a look at this one. We have x to the 4th minus 6x to the 3rd plus 22x squared minus 30x plus 13. It equals 0, which means we want to solve for x. So we want to first list all possible rational zeros. So we're thinking P over Q. I want to know what is P and what is Q. Looks like P is our last number, so 13. Q is our first number, which is 1. And so we've got 1 times 13 to get us 13. Q is just 1 when we're thinking P over Q. Since everything's going to be over 1, there's not going to be any potential fractions. So it'll be plus or minus 1, plus or minus 13. All right. So I'm going to go ahead and I'm going to start with the number 1. To do my synthetic division, I'm scanning to see if I have any missing terms. Doesn't look like I do, so we'll have 1, -6, 22, -30, positive 13. I'll drop the 1. 1 times 1 is 1. Add that up, I get -5. -5 times 1 is -5. Add those up, I get 17. 17 times 1 is 17. Add that up, I get -13. And -13 times 1 is -13. Add that up, I get 0. So started off right away. We got one of our answers. So x equals 0, x equals 1 is one of my zeros. All right, I'm going to write this as 1 degree less. Notice that the degree I started with is 4, so that means that we should have 4 zeros for our final answer. So 1 degree less means that I've got now x to the third minus 5x squared plus 17x minus 13. It equals 0. It is not an x squared term, which means that I have to go through the process of doing synthetic division again, so I can then try to get it to a quadratic, where then I can either factor or do the quadratic formula. All right, so the fact is I technically can start all over. With all my possible rational zeros, this is a new function. So once again, look at the last number, it's 13. Look at the first number, it's 1. So 13 over 1 means that, once again, these possible zeros that I listed up here are also going to work for this second polynomial. So I'm going to kind of start all over again. I can start with a 1 again, and we can see if we're going to end up with a 0. So now we'll have 1, -5, 17, -3. So I'll bring down the lead coefficient. 1 times 1 is 1. Add that up, I get -4. -4 times 1 is -4. Add that up, I get 13. 13 times 1 is 13. Add that up, I get 0. So luckily for us, we got then another answer, but it is the same number. So I don't have to list that 2 times, but understand that, like, if we were to graph it, we have a multiplicity of 2. So that means that at 1 on our x-axis, we would have to touch and turn if we were to graph this. But now I have 1, -4, and 13, and those are going to help form our quadratic. So we have x squared minus 4x plus 13 equals 0, which means we don't have to do synthetic division anymore. We now can either try to factor or do the quadratic formula. Well, I can't find numbers that multiply to 13 but add to -4. So it looks like the quadratic formula is what we're going to do. So once again, -b plus or minus the square root of b squared minus 4ac, and that whole thing is all over 2a. So a is 1, b is -4, c is 13. So we'll have negative and then -4. Plus or minus, under the square root, we'll have -4 quantity squared minus 4 times 1 times 13. And that whole thing is all over 2 times 1. Well, back-to-back negatives means we'll have a positive 4 on the outside. Under the square root, -4 quantity squared is 16. When I multiply -4, 1, and 13 together, that's going to give me a -52. That's all over 2. Subtract those numbers under the square root, and under the square root, now we're going to have a number of -36. Well, under the square root, we have a negative number, which means that we really have an imaginary number. So when I have an imaginary number, that means that we get to put an I on the outside, but then we also are taking the square root of 36, which is a perfect square. So that means that technically that whole thing is going to turn into 6I, and this is still all over 2. So then we can break this apart. It's 4 divided by 2 plus or minus 6I being divided by 2. Well, 4 divided by 2 is 2 plus or minus 6I divided by 2 gives me 3I. So we should have 4 answers. The plus or minus sign with the complex number does give me 2 solutions. Remember, x equals 1 we had twice. So I do technically have 4 solutions, even though I only listed 3 numbers. I know I didn't point it out on the last problem, but notice that, like here, this imaginary number isn't a rational zero. That's why this 2 plus or minus 3I is not something that's listed when we were thinking about p divided by q. When I go back to this last example, because we were dealing with square roots, that also was not a rational number, okay? So, well, it's not a possible rational zero because we're talking integers, okay? P and Q are integers, okay? So that's why that wasn't a possibility list out to us. But it doesn't mean that just because we don't list possible rational zeros doesn't mean that these crazy things aren't actually a part of our zeros. Okay, so I would suggest that you pause the video and try to find all the zeros for f of x equals 2x cubed minus 5x squared minus x plus 6. Okay, hopefully we need to get 3 zeros. When I list all my possible rational zeros, since p was 6 and q was 2, I am going to have a couple of fractions. I started testing numbers and I went up towards positive numbers to get my first zero. I was able to get then a factorable quadratic. So I did end up with a fraction for an answer, but 2, -1, and 3/2 were my 3 zeros. Okay, so that's us using the rational zero theorem to find all possible rational zeros, finding zeros, and then solving these polynomial equations.